Swayam Prabha. Digital India. Educated India.
Next we study about Hilbert spaces. A Hilbert space is nothing but a complete inner product space. Definition: a complete inner product space is called a Hilbert space. So if let X be an inner product space, when we say X is complete, that means every Cauchy sequence in X must be convergent. So let Xn be a sequence. Then we say that then Xn is said to be Cauchy. If for every epsilon positive there exists a natural number n0 such that norm Xn minus Xm is less than epsilon for every Mn bigger than or equal to n0. Here the norm is nothing but the induced norm. Induced norm. Induced by the inner product. Okay, so let us see a few examples. We know that every finite dimension nonlinear space is complete. So in particular, when you take X to be a finite dimensional inner product space, it must be a Hilbert space. Is a Hilbert space. In particular, we can take X to be R power n and the field is R. We know how to define the inner product here. X is x1, x2, so on xn, and y is y1, y2, so on yn. So inner product X with Y is summation xj yj bar, yj. Similarly, when you take X to be C power n and the field is C, you take Z as z1, z2, so on zn, and w as w1, w2, so on wn coming from X. So we know the inner product of Z with W is defined as follows: summation j equal to 1 to n zj wj bar. Another important example, let us take X to be MNC, set of all n by n matrices. n by n complex matrices. So for AB in X, let us define a function like this as trace of AB star. Then we can show that this is an inner product on X, and the induced norm is nothing but trace of A star power of. So this is the induced norm. This is the inner product. With respect to this inner product, set of all n by n matrices is a Hilbert space. Okay. Let us look at few more examples. Let us take X to be L2 of n, X is xn, y is yn coming from X. We know that the inner product is defined as follows: summation j equal to 1 to infinity xj yj bar, and the induced norm is nothing but generalization of the Euclidean norm. We can show that this space is complete, hence it is a Hilbert space. X is a Hilbert space. Here if you look at C00, which is subset of X, we can show that C00 is incomplete, hence we can say that this is not a Hilbert space. So this is a Hilbert is an inner product space. Which is not a Hilbert space. On C00, we have the same inner product as L to N. So with respect to that, this is not a Hilbert space. Okay. Let us look at one more example, which is a generalization of all these examples. In particular, let us look at L to AB. So if I take F1G from L to AB, we have defined inner product of F with G as integral A to B F G bar d lambda. Lambda is the Lebesgue measure. And the induced norm is integral A to B mod F square d lambda power of. You can show that this is also a complete inner product space, hence it is a Hilbert space. Is a Hilbert space. We can also show that CAB, which is a subspace of L to AB, is not a Hilbert space. Here again we have to look at the same inner product as in L to AB. So we can still generalize this example 3. So let us look at X sigma mu be a measure space. That means X is a non-empty set, sigma is the sigma algebra on subsets of X, and mu is a measure on sigma. So we can define L2 of X sigma mu as in the earlier case. This is set of all functions from X to C. F is measurable, and integral of mod f square d mu is finite. So if you take fg from L to X sigma mu, so we can define the inner product as integral over X f g bar d mu, and the induced norm in this case is nothing but integral over X mod f square d mu. So this is the induced norm. This is the inner product. So we can also show that this is a complete inner product space, hence this is also Hilbert space. This is a Hilbert space. Okay, so these are few examples of Hilbert spaces. Thank you very much.